There are a number of factors that are going to affect how acidic a material is, and we're going to talk about 3 of them. For any material with an acidic hydrogen, the bond between that acidic hydrogen and whatever atom it's connected to is going to be polar to some degree. And more polar means more acidic. In a highly polar bond, more of the electron density is removed from that hydrogen, making it more like a bare proton. The second factor is the bond strength between the acidic hydrogen and whatever it's bonded to. And the weaker that bond is, the more likely that H+ is to dissociate. The third factor affecting acid strength is the stability of the conjugate base of that acid. And the more stable the conjugate base is, the more acidic the original molecule was. So in this context, stability is basically referring to how much the base can distribute the negative charge. The conjugate base of an acid is typically an anion, so how easily that negative charge can be spread out over the entire conjugate base molecule is what we're referring to as stability. There are a number of ways that the charge can be distributed. It can actually be reduced by resonance stability, that is, the negative charge is split up over a number of different atoms, giving partial negative charges. Or it can be distributed by spreading it out over a large area, as in the case of things like chloride and bromide and iodide ions that are the conjugate bases of the strong acids. The negative charge is spread out over the volume of those monatomic ions. And we can put these factors into a bit of context and see how they affect the strength of different types of acids. So, binary acids are a type of acid that has only 2 elements. And the most common example would be something like HCl. When you're talking about acid strength, you could also think about things like methane, the CH4 molecule, or H2S. Binary acids, that is, hydrogen with one other element, are going to have a variety of different acid strengths. And we can talk about acid strength in terms of periodic trends. So within a group, bond polarity is the most significant factor. So if we look at the second row of binary acids, we have methane, ammonia, water, and HF. The CH bond in methane is effectively nonpolar. And the HF bond in HF is extremely polar. And we saw earlier that the more polar your HA bond, your H to whatever bond, the more acidic your material is. And that's definitely true in this example. Methane is not an acid at all, and HF is a weak acid. Obviously, this trend is a little bit complex because we know that ammonia is also a base, and we know that water can kind of go either way. So this trend is not particularly clean, at least with the second row elements. And we can also look at trends within a period, that is a column going up and down the periodic table. So within a period, the bond strength is the most important factor. We'll look at the binary acids containing halogens. So HF has the strongest bond, and HI has the weakest bond, and we can see that HF is a weak acid, and HI is a strong acid. So with HF, even though it's extremely polar, it's going to have the strongest bond due to the fluoride ions' very, very small size. And HI is going to have the weakest bond due to the I- ions' very large size. And then within a period for binary acids, you can also consider conjugate base stability. The conjugate bases for the extremes of this column are the F- ion and the I- ion. F- is relatively a less stable conjugate base than I- because that negative charge is spread out over the volume of a fluoride ion, which is very small, so that negative charge is fairly concentrated. And in the I-, that negative charge is spread out over the entire volume of the iodide ion, which is quite a large ion. The next example we'll look at are the oxyacids. So an oxyacid is just a material with this kind of structure, where you have some generic element singly bonded to an oxygen, singly bonded to the acidic hydrogen. And as Y, this generic element's electronegativity increases, the acidity increases as well, because it makes the OH bond more polar. And the acidity also goes up as electronegativity of Y increases, because it makes the conjugate base more stable. Remember that electronegative materials want to attract a negative charge. And then as you add additional electronegative elements to Y, the acidity also goes up. And this happens for pretty much the same reason. You're increasing the polarity of that oxygen-hydrogen bond with each electronegative element that you add, because it's pulling more electron density away from that hydrogen. And in addition, adding extra electronegative elements stabilizes the conjugate base, as described earlier, and it can also sometimes stabilize the conjugate base by resonance, as is the case with the examples I'm going to show now. And now I've omitted all of the lone pairs of electrons from this example kind of for clarity and length of time, but you could go back and write them all in, and you could see how when you remove the H+ ion, you can draw resonance structures for some of these molecules that are going to spread out the negative charge of that conjugate base that forms. Based on the Kas, you can see that as you add more and more electronegative elements to Y, that is the chlorine in this case, your acid becomes stronger. The final example we'll talk about are the carboxylic acids. And these are really just a subset of oxyacids. And they're worth considering on their own because they're just extremely common types of acids, and they're among the stronger of the weak acids. And really, the explanations for why these are fairly strong acids is the same as for the generic oxyacids. So the addition of that carbon to oxygen double bond, that's adding an extra electronegative atom. And when you dissociate that H+ ion, you have resonance stabilization of the conjugate base.